So one of the reasons it's useful to visualize things as vectors, data sets as vectors, is it helps us visualize the concept of orthogonality. Orthogonality is a very important concept in signal processing as well as in understanding the relationship of measured data um, and signals. So orthogonal signals and functions, basically orthogonal means perpendicular. So if we had two lines that were perpendicular, they would be orthogonal. So in vector representation, the orthogonal signals would have orthogonal vectors. What this means is that the scalar product between these two signals, and this is how we generalize for n-dimensional space, the scalar product will be zero. So if two vectors are orthogonal, or if two data sets are orthogonal, their inner product or scalar product or dot product is equal to zero. So let's enlarge this so that we can see it a little bit better. So an important characteristic of signals that are orthogonal, in other words, if they're orthogonal, they're also completely uncorrelated, is that when they're combined or added together, they don't interact with one another. So an example of this in nature might be something like the signal in the frontal lobe of my brain, if I were to record that, and the signal that's being generated by eye movements. These probably would not be completely orthogonal because when the measurement was made, I would probably have some component of eye movement that showed up in the EEG in the frontal lobe of my brain. So, and they would interact with each other because if I move my eyes around, that would cause the EEG in the frontal lobe of my brain to appear to be more active, even though it's not. It's the eye movement noise showing up. That's an example of two signals that would interact with one another. Orthogonality simplifies a lot of calculations, and a lot of analyses couldn't be done if we didn't have the concept of orthogonality. And orthogonality is not limited to two signals, so you can have whole families of signals that are generated that can be orthogonal or even orthonormal. Now, orthonormal vectors are orthogonal vectors, but they have a special quality, and that is they have unit length. The reason that's important is that it allows us, if we want to think about, if we have a signal and it's comprised of several orthogonal vectors, then we can, if the vectors are normalized, then we can get a good idea of how much of a given orthogonal signal or vector is in our signal that we're measuring. And that sort of forms the basis for Fourier analysis and wavelet analysis and a number of other kinds of analyses that are done with families of functions. So as an example of thinking about orthogonality, let's generate a 500-point 2 Hz sine wave and a 4 Hz sine wave of the same length. And let's make our length 1 second. And the question is, are these two waveforms orthogonal? So the approach is going to be that we're first going to create these waveforms in MATLAB. And then we're going to find the scalar product of these waveforms. If the result is near zero, the waveforms are orthogonal. Now, here's sort of one example of where computational techniques are not perfect. Because of rounding errors in significant bits used in a MATLAB calculation, sometimes you will not get a true zero. Also, because you have digitized your data, you have added some frequency components to this 2 Hz sine wave, and we'll talk a little bit more about that when we start talking about Fourier analysis. But because you don't have a perfect continuous waveform, you are probably not going to get perfect orthogonality. All right, so the next slide is going to show our MATLAB code. So here's where we set up our sample interval. We're going to sample every 0.002 seconds, and we're going to do that 500 times, and 0.002 times 500 is going to give us 1. So 1 second is our record length. And now we're going to set up our time vector. And the way we set up our time vector is we go from t equals 0 to t equals n minus 1. Okay, let me talk about this for a minute. In MATLAB, the indexing in MATLAB is not like C, if you're familiar with C. With C, the indexing starts with 0.0. In MATLAB, the indexing always starts with 1. So if you have a 500-point data array, the way you reference your first point is that it's 0.1. So if you were going to plot that representing time, you would not be able to get 0. So basically, we have to set our time vector up, instead of being from 1 to n, we set it up from 0 to n minus 1. That gives us the same number of points. It's just that now when we plot it, we're going to start at t equals 0. We then take that 0 to n minus 1 and we multiply it by our sampling time, and what that does is that converts us to seconds. So 500 has units of sample, 0.002 has units of seconds per sample. And when we do that conversion here, our plot's going to give us a plot as a function of time. So we take our signal F1, which has a frequency of 2, and our signal F2, or a frequency of signal 2, is 4. And then we set up our sine wave. So basically we have our vector t that represents time, and we take 2 pi times F1 times t. And we'll set that up as signal x. And then as signal y, we have 2 pi times F2 times t. And then we're going to take the correlation, which is basically summing x times y point by point. And we'll then use the display correlation, and that will give you the result of the correlation value. So if you do that, you get 1.96 times 10 to the minus 14th, which is effectively 0. So we would expect this because since this is a sinusoid and they are harmonics of each other, they're known to be orthogonal. If you have not had a course in Fourier analysis, you might not know that, but the sine of 2 n, or of n omega t, is 2 pi n omega, or 2 pi n ft, where n is an integer, are considered orthogonal waveforms. And sine waves are orthogonal to each other. So, like I said, if you haven't had a course in Fourier analysis, you may not know or remember that. All right, so based on this idea of orthogonal functions, we can do transforms that are essentially a remapping of original data into something that provides more information. So most of the transforms here are basically achieved by comparing a signal of interest with some sort of probing function or family of functions that's termed a basis. And usually the basis function is a lot simpler than the signal, so it's often a sine or cosine wave or a series of sine or cosine waves. So quantitatively, a quantitative comparison can tell you how much your complicated signal is like a simpler basis function. And we do that using correlation. So if f is our family of functions, let's say we take the first one, so let's say the first function is sine of omega t. If we take point by point that function and find its correlation with our signal, we get an idea of how much of this function is present in our signal. So one example of where this might be useful is, let's say we're concerned that we have 60 hertz noise showing up in one of our signals. We could do a correlation of our signal with 60 hertz and determine how much 60 hertz signal is present in our signal that we've measured. In the continuous domain, this is done through integration. Now, obviously, you can't have a mismatch between your signal and the length of your basis function. So what you have to do if your basis function is shorter is you have to truncate your signal down to the same number of points. So you cut out some portion, or you multiply the signal by another signal that zeroes it out outside the desired portion. So we can use a waveform, we can use windowing functions that we talked a little bit about previously. So here's an example of a waveform, and if we need to reduce the size of the signal, we can use a windowing function, and this example is a Kaiser window. So we're taking this waveform and we're multiplying it by this waveform, so that basically our windowed waveform is going to be much smaller. And so now basically what happens is the correlation becomes the correlation of our signal, the correlation of our basis function, and then the windowing function is included in there because remember um, it multiplied the signal. So it's also possible to do a sliding comparison. And this is done sometimes if your probing function is a lot shorter than your data function. And so in this case, the shorter function slides along the longer function, and you do a correlation made at every position. So this is called a cross correlation, and mathematically it's represented, here's your signal, and here's your probing function, and then K is basically stepped through all the values from 1 to n so that you're sliding this waveform across f of n. So you basically have a correlation done at one position, and then you slide this function, you do a correlation at another position, and then you slide it, you do it at the third position, and so on. And so what comes out is not a single number. What comes out is a function, and that function is related to the position where the window was, where the sliding window was when you did the correlation. So it's possible to use both the window and slide in one operation, and this is often called a short-term Fourier transform. So in this case, you have your window, and you have your data, and you have your probing function, and it's the window that's actually accomplishing the sliding. So here's an example, this figure here, where we have a probing function and a signal. And basically this probing function is at position 0. And then what we're going to do is we're going to move it and do a correlation, and we're going to move it and do another correlation, and we're going to move it and do another correlation, and so forth. And then what's plotted on this lower graph here is the correlation between this function and between the probing function and our signal function as a function of where the probing function is located. And so what we find is that right here at 0.325 seconds, we have the maximum correlation value. So that would be about right here. So when this probing function is here at about 0.325, and we're talking the beginning of the probing function, so this peak here would be located almost at 0.4. And you can see the shape of this probing function waveform and the shape of our window waveform look very similar there. So when it reaches a certain point, the correlation peaks, and then once the frequency of our signal gets higher than our probing function, then our correlation begins to drop. The correlation oscillates, and the reason is that obviously there are points where this peak is in phase with one of these peaks and points where it's completely out of phase with one of these peaks. And so that's going to make your correlation go from a high positive to a high negative when that happens. So there are other correlation analyses, correlation and covariance. So covariance computes the variance that's shared by two or more waveforms. So basically what you're doing is, the only difference is, it's just like the correlation, except in this case, you're subtracting out the mean. So you have your x value, and you've subtracted the mean of x. You have your y value, and you've subtracted the mean of y. And then you're taking the same sum. And now we're going to normalize that by dividing by n minus 1. 1 less than n. When sigma xy is the covariance, and x and y are the x bar and y bar are the mean, and x and y are the signal. Another variation of this is the Pearson correlation coefficient, and the nice thing about the Pearson correlation coefficient is this normalizes the covariance. So basically, for the Pearson correlation coefficient, you use the covariance divided by the square root of sigma x squared, sigma y squared. So sigma x and sigma y are the variances. This is the covariance equation. And the reason this is nice is it gives you an outcome between plus and minus 1. And so that gives you some idea of, if you're working with multiple signals, sort of a frame of reference for how they correlate with each other.